A very good morning, good afternoon, good evening to all the participants and the candidates who are taking this course under NPTEL MOOC. And the title of the course, as you can see, is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you know, the course follows three different broad areas. One is forecasting, the next one is regression models, and third one is time series analysis. And here we are starting the third week, which is basically the 11th lecture, and the main focus continues to be in the area of averaging techniques and forecasting methods. So, this is the week number and the lecture number. Now, what is the coverage of this course? If you remember in the last two classes, which was the 9th and the 10th, and which were the second last and the last class for the second week, the main focus was on moving average. Moving average considering the 3-month moving average, 2-month moving average, 5-month moving average, 7th-month moving average. We considered the formula. We also considered the formula where we had, say for example, 2 by 3, where you are taking moving average for 3 months and you are taking such 2 blocks, or you can also consider 3 into 4, which means that you are considering 4 such months as a block, and such blocks you are considering 3 in number. Then we also considered the concept or the idea of, say for example, 5 into 4 into 4, which means that you are taking a block of 4 months, taking 4 of those blocks at one go, and you are repeating it 5 times. Now, based on that, we considered one problem, which was basically trying to forecast the number of international passengers in airline travel between a particular time frame in years. And using these two formulas, we plotted different moving averages. And the last diagram which was there, where we spent a lot of discussion, was basically trying to plot y, which was the actual value, and the 3-month moving average 1, 3-month moving average 2, 3-month moving average 3. That means you are taking 3 months at a time, but shifting the block accordingly, and then we found out 3 cross 3, which gave us an idea that it was smoothened out. So, more number of moving averages, that means more number of blocks you take, or number of data points which you have in a block, if they increase, then it is smoothened out. And if you remember, we had discussed in the diagram how the idea of trend was there for in the first 2.5 years, then for the next 3 years it was almost stagnant. The mean was there, but it was not increasing. And then in the third phase of about 2.5 years, it was basically 2 years and 4 months, but we consider 2.5 years. We saw the trend was increasing with respect to the first block of 2.5 years. And we saw there was a cyclicity which was repeating, which I highlighted using the graph. Now, having said that, we also mentioned the idea that we will cover the concept of cyclicity, seasonality, trend, and this is what would be subsequent emphasis in the coming lectures. So, the coverage for this class or lecture, which is 11th one, we will try to cover exponential smoothing average. This is single non-adaptive parameter. Exponential smoothing average or exponential smoothing method considering multiple non-adaptive parameters. The third one will be exponential smoothing considering single adaptive parameter, and obviously you can extend it to exponential smoothing considering multiple adaptive parameter. Now, what I mean by parameters is basically the concept of weights which you had given. So, if you remember, for the moving averages, depending on the number of average or blocks we are taking, the weights would be assigned, and we showed that in the long run, as we keep taking more and more such moving averages, the histogram plot of the weights slowly turns out to be a normal distribution. Now, parameters here I mean by the weights. Now, when I consider the single non-adaptive parameter, it means that in the exponential smoothing average, we are considering there is only one parameter and that parameter is not changing with respect to time. So, any shift in the trend would not be reflected by utilizing the fixed parameter. You have to keep changing the parameter for different models. In the second part is that we will consider non-adaptive multiple parameters, which means that we have more than one parameter, like say for example, alpha 1, alpha 2, alpha 3, and try to basically keep the weights of these parameters in such a way that the sum is equal to 1, and in the end we will take those set of parameters such that the error is minimized. And in the third part, it is exponential smoothing average, where the parameters is also adaptive. Depending on how the values change, the parameter value will also change. And obviously, logic would say that we can extend this work in the case of exponential smoothing average, where there are multiple adaptive parameters. So, this what we will cover, and the exponential smoothing methods covers, as I have already mentioned, exponential smoothing single non-adaptive parameter, exponential smoothing multiple non-adaptive parameter, exponential smoothing single adaptive parameter. Later on, other forecasting methods I am just mentioning, we will cover it as we proceed with the class, would be Halt linear method, where the main emphasis is to find out the trend and do the trend analysis. The next one is Halt winter method, where we have both the concept of trend and seasonality, and this concept of seasonality is considered in the Halt winter first method, which is number 5, as a multiplicative seasonality. That means, the seasonality increases using a multiplicative factor. While the sixth method is also Halt winter method, where we try to find out the trend. Yes, we try to find out the seasonality, yes, but the seasonality does not increase by the multiplicative factor, it is additive, that it keeps adding such that we are able to find out the seasonality. Now, the word seasonality does not mean that it has to be basically only 4 months, because considering the seasons we have summer, winter, autumn, spring in a year, the seasonality concept can come based on the factor, it can be for 1 year also, it can be for 6 months. Like say for example, if you are considering the so called concept of seasonality, even though that can be considered as a concept of cyclicity, there is a cycle. So, sale of warm woolen clothes would be in the month, say for example, we are considering north of India, it will be picking up the volume in the month of September, continue till about January. While if I consider the sale of ACs, fridge, coolers, it will be more during the summers, say for example, the month of April, May, June, July. Now, we will consider the exponential smoothing non-adaptive parameter, and I will highlight it accordingly. So, here it is. So, if you consider again the same concept, I will use different colors. So, we will consider y as with the suffix t as the actual value. We will consider f suffix t as the forecasted value, where the suffix t would denote the time frame. And we will consider the idea that there is a one parameter which is given by alpha without the suffix, because alpha is fixed and hence it is non-adaptive. So, the formula basically becomes that if I have the time frame, I will utilize the black line to denote the actual value. So, you have these values denoted by y. So, this is y t, this is y t minus 1, y t minus 2, and it will continue. While if I draw the forecasted values, I am just drawing a line in order to denote, and we will come to the example very soon. So, if I have the f values, So, obviously, we will have F t, which is the forecast for y t. Similarly, we will have F t minus 1, which is the forecast value for y t minus 1. We will have F t minus 2, which is the forecast value for y t minus 2. Considering this, the formula is as follows. So, I want to find out f t plus 1 for the next time period, considering I am standing today, and I also have the actual value for today, which is y t, and also have the forecasted value based on the past data, which is f t. So, I will assign weights, and this is where the weight concept of non-adaptive concept comes. So, I assign a weight of alpha to y t. So, higher the alpha means more the weightages I am giving to the actual value, and the corresponding weight which would be for f t is basically alpha 2, which is, because if you remember, alpha 1 plus alpha 2 is 1. So, alpha 2 can be replaced by 1 minus alpha. So, 1 minus alpha would be the weightages for f t. So, if I give a weightages of 50% for alpha, which means I am giving 50% weightages to f t and 50% weightages to y t. If I consider alpha as 90%, so I am giving 90% weightages to y t and 10% weightages to f t, which means the actual value has much more implications for the forecasted value, which is f t plus 1. So, here what I have explained, I am just writing. So, y t is the actual value, which we have already mentioned. F t is the forecasted value, which has been also mentioned. And here, as per the nomenclature, we are considering E t. E t is basically the error. So, error for time 0 would be y 0 minus f 0. Error for time period 3 will be y 3 minus E 3, and we will continue. And alpha is the weights are chosen such that the mean squared error is minimized, which means the variance you are trying to minimize, which is the dispersions you are going to minimize, which is basically the fundamental property we try to utilize when we try to find out how to find out the error. Now, the question may arise, can we use other measures in order to find out the errors and minimize it? Yes, we can, because if you remember, we had the percentage error, weighted percentage error, weighted mean squared error, absolute error, weighted absolute error, U statistics, everything had been utilized. But I have just written it in the sense that mean squared error is minimized because it makes sense to make other people understand that what is the error. Error is basically the dispersion. We are trying to basically minimize it and bring all the fluctuation as close as possible to the central value, which means the error is 0. Now, let us take a data set and solve the problem. So, this is the single non-adaptive parameter, and this is the example number 10, as you can see in the slide. So, in the first column, we have the month. Second column, we have the y t, which is the actual value, and based on alpha. And what is alpha? So, in the first case, we are taking alpha as 0.1. In many of the problems, when you solve, it can be also considered as 1 minus alpha, because it would not make any difference, because alpha plus 1 minus alpha is 1, and alpha is the only parameter based on which you can immediately find out what are the weights for corresponding values of y t and f t. Next value of alpha is 0.5, and that last one is 0.9, which is 10%, 50% and 90%. Now, what you do is that according to the concept or the idea, you consider, if you are starting from January, you consider the best predictor for the next month, which is February, would be the past actual value. That means 200 is the value for the month of January. So, it will be considered that f t, whatever the alpha value is 200. So, if you see in the slide, it is marked in blue color, and the arrow has been given in order to emphasize that fact. Now, based on that, we can find So for example, if I consider the weightages would be given correspondingly. So if I have the values, so consider for the month of February. So month of February is given, and based on that, the second column is already given because this is the actual value. We want to find out the forecasted value. So technically, if I consider 165, so because it is 50%, so it will make sense, and we'll be able to understand. It is 167, which means I am taking 50% means 200, which is FT for February, plus 135 by 2, which is 335 by 2. 2 ones are 2, 2 6 12, 167.5, which is what we have here. So I have given equal weightages to February actual value, February forecasted value. Based on that, I find out the forecasted value for month of March is 167.5, which should be compared with the actual value for March, which is 195. So if I want to find out the error, it will be, the error would be, I'll use E as the error, and using red color, it will be 195, which is here, 0.0 minus 167.5, which is here. I get the error, and you can find out the error. Now if I move to month of March, but considering I am going to take 10%. So if I consider 10%, so the corresponding value would be 0.1 multiplied by 135 plus 0.9 multiplied by 200, where 200 is the forecasted value for February and 135 is the actual value for February. So this would become 13.5, and this would become 180.0, hence the value becomes 193.5 as marked here. And if I consider the error, I am using again the red color. So error would be 195.0 minus 193.5. And if I go to the last case, I'll use a different color. So here in this case, I am using the blue color in order to denote the third column value, the last column values, fifth column values. So that will be given by the concept that you have 90% value on 135 plus 10% weightages to 200. So if I find it out, 9 5s are 45, 4 9 is a 27, 1 are 3, 12, and this is 20. So this becomes 141.5, which is given here. And if I want to find out the error, I'll use a different color. See, for example, violet. So the error for this case would be, actual value is 195 minus 141 0.5. Now, if you see interestingly, the more the weightages you give to depending on the values you want to have, whether you want to give more weightages to the actual value or more weightages to the forecast value. So, if you give more weightages corresponding to alpha, depending on what you think how the trend is, you can find out the value for alpha which will minimize the error. Now, what I mean by minimizing the error is that all the errors which you find out as you marked in the red color or marked in the violet color, red one being for the third column, violet one being for the fourth column, and I can continue, which means that the next value of error in the last column would be basically given by 197.5 minus 189.7. Then the difference is 310 minus 196.7 and you have all the errors. Square the error, find out the average and try to minimize. Or else, as I said, you can consider the absolute error, the weighted error, and corresponding to those values you can utilize the metric which you think is the best for this problem. Now, if I consider the error which is shown in red, which is basically for the third column. So, the errors would be, I will use the red color. So, it will be 197.5 minus 193.7, next value is 310 minus 194. Again, I have the errors, I can square them, sum them, find out the mean value. I can give weightages to find out the weighted squared errors, average of the weighted square errors. I can find out the absolute error, I can find out the weighted absolute error, and based on that I can proceed. Now, here in this slide, I will erase all these things. So, let us not make it too cluttered. So, if I continue, I plot the diagram and here is what is plot. So, the quantity which is yt is marked in yellow. So, this is the yellow line. If I find out the forecast value for 10%, the red line is there, and you see the difference between the yellow and the red line. There is a lot of difference. That means, if I consider the weightages as 10%, as you have seen in the last slide, it would not make sense because you are being far removed from the actual value, which is the yellow one. For the blue one, where you are giving 50% weightages to both the actual value and the forecasted value, which is yt and ft, the blue is much better than the red one. But interestingly, if I basically give weightages of 90%, as you saw in the last column for the last slide, here the green line almost mimics the yellow one, but with a shift, and the shift is obviously because you are trying to predict for the next time period. So, if I consider technically from this diagram the concept of error, there are obviously would be the so called from pictorial analysis, we can say the error would basically be the minimum for the green line. Now, let us come to the fact of the exponential smoothing, where I am considering the multiple non-adaptive parameter. By the way, I have in the last slide, if you remember, I have taken the weights as 10%, 50% and 90%. So, you can draw all the weights starting from 5% to 95% and plot them, graph, plot the error, plot the square of the error, find out the minimum of the error, give weightages, and try to basically find out which concept of the weightages, one parameter weightages, will give you the best prediction. Now, let us come to the exponential smoothing average, where multiple non-adaptive parameters are there. So, parameters are there, but they are more than one. There it was alpha, and obviously the other one was 1 minus alpha. Now, it is more than one. So, that means it can be alpha 1, alpha 2, alpha 3 and alpha 4 also. But the idea remains that the sum of all these alphas, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is always 1. That is one important constraint. And obviously, you will choose those sets of alpha or that particular set of alpha 1, alpha 2, alpha 3, alpha 4, which will minimize your error. Here I am considering the error concept is being given by mean squared error, or the other concept which I mentioned like weighted mean square error, absolute error, weighted absolute error, percentage error, weighted percentage error, U statistics, whichever you think would basically give you a better understanding of the forecasting model. Now, remember in the U statistics that concept was there. If U value is 1, U value is less than 1, U value is greater than 1. If U value is less than 1, then your forecasting method is better than the naive method. If U value is equal to 1, then your model and the naive model are almost giving the same answer. And if U value is greater than 1, obviously I will be more happy to use the naive method. Naive method means the value of the forecast of today would be the best predictor for the actual value for tomorrow. That means so called expected value for FT would basically be the value of YT plus 1. Now, here also again we consider the same nomenclature. Y is the actual value, F is the with the suffix is the forecasted value, and E is the error term. And if you remember and if you see it, the parameters are non-adaptive are alpha 1, alpha 2, alpha 3 and alpha 4. Now, obviously, it is true that the sum of alphas is equal to 1, which I have already mentioned. And if you remember and if you see the weightages which you are giving to, I will use a different color here. The weightages if you give to YT and YT minus 1 is basically given as alpha 1 and alpha 3. And the weightages which you will give for FT and FT minus 1 are alpha 2, alpha 4. So, alpha i's are between 0 and 1 where I is equal to 1, 2, 3, 4 weights which should add up to 1, which I have shown, such that we can use the MSE or the U statistics or the MAPE or the MPE or the ME, it can be considered. Some other constraints can be that the weightages are increasing, in the sense if I consider the actual value, I would like to put more weightages for the actual value, which means alpha 1 would be more than alpha 2. Actual value weightages for T time period weightage is more than the T time period forecasted value weightages. Similarly, weightages for YT minus 1 is more than the weightages for FT minus 1. That can be one of the constraints. Other constraints can be I want to find out the weights in such a way that the differences of the actual value and the forecasted value is less than some epsilon, that is depending on the accuracy of the model. So, with this I will end the 11th class and continue discussion about the exponential smoothing multiple non-adaptive parameter methods further on. So, the slide with which I am ending this 11th lecture would be the starting slide for the 12th lecture, because if you remember for all the other classes till the 10th lecture that has not happened, because the discussion was going on in depth. Hence, I took some time in trying to explain the non-adaptive one parameter, and I also think the non-adaptive multi-parameter multiple parameter needs time for discussion, hence this slide will continue in the 12th class. Thank you very much and have a nice day.